Today I want to talk a little bit more in depth on electron configurations because we as chemists are interested in the outermost electrons. They're the ones that do all the cool and interesting chemistry, and we teach you how to do electron configurations and then we send you on your merry way. But I want to get into a little more in-depth look at electron configurations, talk about some notable exceptions, talk about how this looks in ions, and kind of go from there. So this is going to be a little bit of a hodgepodge of a video, but it's really just electron configurations at a higher level than we usually do it for like an introductory course. So we're pitching this at a higher level than that. Okay, so let's just remind ourselves about electron configurations. Let's look at bromine. If we look at bromine on the periodic table, it's one of our halogens. It's number 35. So a neutral atom of bromine has 35 electrons to work with. So if I'm using the periodic table, or if I'm using the Aufbau Principle, or the building up principle, then I know that I start through the first, and the first part of this is going to be 1s2. That gets me through the first period. Then I'm going to have, through the second period, I go through my S block, and then I go through my P block. So that would be 2s2, 2p6. Now bromine is still down in period 4, so I have the entire third period to get through too. So that would be 3s2, 3p6. And then we're going to go through the 4 s's, 4s2, 3d10, which gets me through zinc. And remember that the D block starts with 3 because it's technically, electrons are in the third shell technically. And then we're going to count over in our P block from gallium. So 1, 2, 3, 4, 5. 4p5. Okay. So once we start getting into the elements that have D block electrons, so once we get past kind of those second and third period, first, second, and third periods, and we get into things that start going through the D block, then when I start thinking about the noble gas configuration or the abbreviated configuration, then I'd say, well, here's my periodic table. I'm going to go up to the noble gas prior to, that would be argon in this case. And I'm going to put argon in brackets, and that's going to account all the way up through the 3p6, right? That's argon. And then I'll say, here's the rest of it. This is the way that we teach you to do it. 3d10, 4p5. Now, if you move this around to the order where it actually makes a little more sense, because the n's, the principal quantum numbers, line up, then now we have a way to really easily identify the valence electrons on these things. So here, we would call this my noble gas core, right? Because it's the noble gas that makes up all of this stuff. But when we have d electrons there, and we sneak them in front of the s that's there, this entire thing is called the pseudo-noble gas core. Pseudo-noble gas. Okay, so the pseudo-noble gas core then is composed of the noble gas that comes prior to that element in the periodic table and all of the d electrons that you go through in order to get to it. That leaves you then the valence electrons. So it's an easier way to identify them. Your valence electrons for the main group or representative elements are always going to be those highest energy S and P's, so that gets them kind of organized together. So you will sometimes see this notation, and I just wanted to draw your attention to it because we usually will just teach it, it's this way, and this is the order, and this is the Aufbau principle. But if we kind of rearrange it, then this is just another way we can think about the electron configurations symbolically, which help us to delineate kind of what are closest to the nucleus, what are the ones that aren't really participating in the chemistry, and which ones are. So that's kind of the way that we do that there. Now, of course, there's exceptions to the Aufbau principle. Of course, there's exceptions to the way that we would normally think about electron configurations because it's chemistry. So let's look at chromium here. Chromium is number 24 on the periodic table, so we'll start there. 24 electrons. Now, if we were going to write it all out, then we could, and let's do, for practice, 1s2, 2s2, 2p6, 3s2, 3p6. So that gets me through argon. And then if I'm looking at period 4, which is where my chromium is, then I'm going to go through the 4s2, and then I'm going to count over in the 3d block 1, 2, 3, 4. So 4s2, 3d4. This would be my predicted. Based on what we know about the Aufbau Principle, based on what we know about the periodic table, everything that we've learned so far says that this should be the predicted value of this. This should be the electron configuration. But it's not, because science is never simple. So let's abbreviate this thing down to argon. That covers all of this. 4s2, 3d4. So there's my predicted. My actual is argon with only 1 in my 4s and then 3d5. This kind of goes to Hund's rule, which says that electrons like to spread out as much as possible. So they're going to like to spread out to give themselves as much space as possible. If we're picturing this on kind of our energy diagram, and here's my 4s, and here's my 3ds, then predicted I'd have a pair here and 4 in this guy. But my actual says I have 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. And they're all spread out. So because these things are so close in energy, right, the principal quantum number leads you to believe that this should be lower energy than my 4s, but they're so close, energetically speaking, that it kind of acts as another electron orbital in this chain. So it's happier to spread out than it is to pair up. And this actually leads to some interesting characteristics about chromium and when it forms ions and all that good stuff. So this is one exception. Now, because we know what we know about the periodic table, which is things that are in the same columns have the same kind of characteristics, and the reason for that, of course, is because of their same electron configurations, then you'll find that this pattern holds up with everything below chromium as well. So molybdenum, tungsten, seborgium, these guys are all going to do the same thing. Now, tungsten and seborgium have the F block, remember, in between. So there's some weirdness there as well. But these guys will all do that same feature. So this would, molybdenum would be 5s1, 4d5 instead. So same number of electrons, different positioning, kind of interesting, notable exceptions. Another notable exception is copper. So if we look at copper, it's right next to zinc on the periodic table. So it's in the same row. So I'm still in the 3D. And if I was going to predict what copper's is with its 29 electrons, then I would predict that it is argon, because it's in the same row as my chromium, 4s2, 3d9. Right, because when I count over, zinc is the 3d10, right? But instead it's 1 prior to. So that's what I would predict. But what the actual is it does the same sort of operation, and for the same kinds of reasons. So the actual is 4s1, 3d10. Now again, this is one of the reasons that copper likes to form a +1 ion, because it's easier to lose that 1s electron than it is to pull away from those pairs. So that's one of those types of reasons. Same with chromium. Chromium will lose the 1s easier than it is to lose these other guys first. So these are notable exceptions. Now copper is in the same column on the periodic table as the other coinage metals. It's kind of what we call this little region here. Kind of, we have nickel, zinc, copper, and then we have silver, gold, kind of in that area. So copper, silver, gold, they all do the same. I think that's rontium or something like that. These guys all do the same electron configuration. And again, with gold and Rg down here, you have the F block in there first. Okay, so these are going to do the same operation as copper with that same weirdness. So those are some interesting and important examples because they're pretty common elements. Chromium and copper are pretty common. Silver is common as well. And so these are important distinctions to make for our actuals, and these are important notable exceptions. Now, another thing about electron configurations is we can talk about the electron configurations of ions, because ions, of course, are gaining or losing electrons in order to kind of fill a valence here. And when they do that, then we have kind of an interesting pattern. And we have substances then that have the same electron configuration. So the prefix iso means the same, like isosceles triangle or isotopes. And if we have the same electronic structure or the same electron configurations, then we call the structures or the substances themselves isoelectronic. So let's look at an example of that. Let's take neon, for example. So neon is one of our noble gases. It's got 10 electrons. So its electron configuration is 1s2, 2s2, 2p6. There's those 10. Now let's take fluorine. Fluorine has 9 electrons, but when it becomes the fluoride ion, meaning when it gains an electron, then now it has 10 electrons, right? So fluorine normally has 9. I have the extra, so now I have 10 electrons. If I'm doing the ground state of that ion, the lowest energy configuration, then it's going to give me this. There's those 10. From an electron configuration standpoint, I wouldn't be able to tell the difference between the fluoride ion and the neon ion. Or neon. Neutral neon. Neon isn't an ion. Got too excited there. Now let's look on the other side. Let's take magnesium. So magnesium usually has 12 electrons, but when magnesium is magnesium 2+, when it loses those outermost electrons, right, it's 3s2 electrons, then now it has 10 electrons with its 12 protons, giving it that net +2 charge. So now this is going to be 1s2, 2s2, 2p6. Same electron configuration. So these are all isoelectronic to each other. So neon is isoelectronic to the fluoride ion, to the magnesium ion, etc. So these are just examples of that you'll run into. So we can talk about electron configurations for ions, but they can be a little bit misleading. We can also talk about electron configurations for things that are outside of the ground state. So let's talk about the excited state. Now, excited state electrons would be something where we've bumped up an electron to a higher energy level. It's into a new shell, for example. So let's say that I have, let's look at the Bohr model of the atom here. Now we know that electrons, here's my principal quantum number 1 and 2. So if I have a full 1, and let's say I have a full 2, and here's my 3, my nice bullseye here, which if you've seen my videos, you know how terrible of a drawer of circles I am. All right, so let's take this electron configuration we were just looking at, right? So here's my 1s2, 2s2, 2p6. So we have a full one here. Now this would be my ground state. If I put some energy into this, then I might excite an electron up to a higher level, right? And I can do that if I put in the right photon, right? If it's quantized. So if I put in the right amount of energy, then this guy can jump to a higher level. So now it's in the third shell. Now I would have 1s2, 2s2, 2p5, 3s1, right? So now I have something that is jumped to a higher level, and we can recognize the excited state because it looks slightly different than what we would expect for a normal electron configuration, right? Something's amiss. Something's a little bit higher energy than it should be. So we could recognize it that way. As always, if you have any questions, don't hesitate to reach out. Otherwise, I will talk to you again soon.